My project is called Golden Hour Photography in the Visible Light Spectrum. My name is DL Martin, and I am a part of the Pre-Engineering Education Collaborative at Honolulu Community College. Golden hour is an hour to half an hour before sunset, and it varies on season and location. This time is a preferred time for photographers because of the varied lighting, but it is also popular to take selfies on social media during this time because of the golden glow effect. The visible light spectrum are the colors that the human eye can see. And I used a SparkFun spectral sensor that had 6 different color channels: violet, blue, green, yellow, orange, and red, and measured the visible light intensities in irradiance, microwatts over centimeters squared. And I took these readings at sunset and at midday. Sunset to test the golden hour, and midday as a control because of the neutral lighting seen in photographs taken at that time. My hypothesis was that if what we see are the reflections of the sun's light on objects around us, then during golden hour before sunset, irradiance will be higher in red light than blue light, because the distance through the atmosphere is longer, so the blue light will scatter away. And I added a diagram on the side showing how sunset, there's a longer path to get to one point on the Earth compared to midday. Materials and methods. For my materials, I had a visible light spectral sensor connected to a breadboard microcontroller with a quick cable. I had them inside a reflective box that aided in the readings of golden hour and midday. I had a power cable that was inserted through a hole in the side of the reflective box to connect the breadboard to my computer, which aided in data collection, and it also was so that the sensor would turn on. For my method, my hardware assembly was connecting my sensor to my breadboard and my breadboard to my computer and making sure that it was turned on when it was connected to my computer. My software program installation included downloading Arduino to my computer and also downloading the SparkFun library so I could use the example 1 basic readings for all of my that I used for all of my sensor testing and my hypothesis testing. For my sensor testing, I did dark room testing to test whether the sensor had readings when light was put on it and that it had no readings when light was taken away. I tested a reflective box and a white box, and the reflective box was more sensitive to light readings, so I used the reflective box in testing my hypothesis, but I came up with problems with the breadboard LED on light and transmission light interfering with data readings, so I had to cover those lights with tape. Light spectrum measurement procedure was testing my hypothesis, and I had my breadboard and spectral sensor taped inside my reflective box and connected to my computer. I had the reflective box and computer on top of a table about 22 inches off the ground, and I took readings outside of my house for sunset and midday readings. I copy and pasted serial monitor data into a text edit file and converted it to a CSV file so I could create data plots in Excel. And I used the example 1 basic readings from the SparkFun library for all the tests and readings. For my results, I did a sensor sensitivity test at sunset, testing the vertical versus horizontal orientation of the reflective box with the sensor inside. I did this test after I did all of my readings over the 4 days testing my hypothesis, which was only with the horizontal orientation of the reflective box and sensor. So they might not be as accurate because, as you can see on the graph, the vertical orientation had significantly higher readings in red irradiance values compared to the horizontal orientation, and the horizontal orientation had higher violet values in red. So my time comparison for golden hour versus midday averages in the horizontal orientation. Golden hour from 6:30 to 7:17 p.m. about 47 minutes, and midday at 12 p.m. for a couple minutes. I found that midday was relatively even for all color channels, and the golden hour had the highest values in violet irradiance readings and the lowest values in orange. For my day-to-day readings during golden hour, I checked the weather channel, and it said that the 23rd and 24th were fair, meaning that less than 3/8 of cloud coverage were on those days, and they were mostly clear. And the 25th and 26th were partly cloudy, meaning that 3/8 to 5/8 of cloud coverage were on those days, and I didn't acquire any data on the 26th. For the mostly clear and fair days, you can see that the average irradiance for red is significantly higher than the average irradiance for the partly cloudy days, and the partly cloudy days have higher violet readings than the mostly clear days. And on the bottom, I added pictures of the sky during my readings during these days. For my conclusion, violet and blue light had the highest irradiance percentages in the sky during golden hour day to day, but only with the reflective box positioned horizontally. So if I did the data collection with the reflective box positioned vertically, I probably would have gotten more red irradiance values than violet and blue. The highest average irradiance percentages for red were on clear days compared to cloudy days, and the cloudy days had higher violet readings than the clear days. As a result of this data, clear skies aid in higher readings of red light. And this makes sense because according to NOAA, the National Oceanic and Atmospheric Association, they stated that clear skies are better for brilliant sunsets, and that low-level haze and dust do not aid in the Rayleigh scattering of light, which is basically different wavelengths, including the visible light spectrum of light across the sky. For my future work, I would replace the reflective box with a parabolic shape, because a parabolic shape is used in radio towers, and they help in the transmission and receiving of data for a wide range of collection. And I would use a laser pointer to test my sensor calibration, because I did not have the means to calibrate my sensor properly because of COVID, and I didn't know exactly whether it was calibrated correctly. I would also compare different seasons and cities for future work, because winter and fall in the US are said to have some of the most brilliant sunsets, and summer not as much because of the haze and other variables. I would also investigate color distribution in pictures taken during golden hour and compare it to the irradiance values, and possibly create a golden hour synthetic light so that photographers and people can use the synthetic light to take golden hour pictures rather than having to have the best weather conditions to take golden hour selfies or pictures. These are my references, and I would like to give thanks to Mevon, Catherine, Dr. Khan, Mia, Leo, and Anthony for their support and guidance throughout this project. Thank you.